Okay, guys, so we're going to move on to 9A, functions, the building blocks of mathematical models. So basically, this first section is just kind of an intro into or into functions. It's going to give you a little background, kind of the notation, things like that. And then the next section, we'll start working with lines and, actual doing some math, I guess you could say. This is more like definitions and background. So let's get started. So a few things to keep in mind. Functions describe how a dependent variable changes with respect to one or more independent variables. When there are only two variables, they are often summarized as an ordered pair with the independent variable first. And you guys are used to this when we do a graph, right? We have, oops, that's a pretty bad graph. When we do a graph, right, we have the y-axis and we have the x-axis. Usually, we like this to be the independent, and we like the y-axis to be the dependent. It doesn't have to be that way, but in general in math, that's how we do it. And again, there's a lot more to it than we're going to be able to go to in just this section. But you'll see some kind of generalizations done in the notes here. So just keep in mind, there are a little bit of exceptions to this. I might bring it up as we go through them. But some things just aren't worth, we don't have enough time to cover all of the depth of functions. Just to keep in mind, normally when I teach, an algebra class, let's say you're taking math 90 or math 60 or whatever, that's, algebra. Then you learn about functions in algebra. Then you take intermediate algebra, you learn about functions again. Then you take college algebra. Guess what? You learn about functions again. Guess what? When you take calculus, you're working with functions again. So there is a lot to functions, and we're only going to be covering it in a few sections in this book. So remember, there's definitely a few things we're leaving out here, but we kind of got to pick our battles, so to speak. Okay. So in general, when they say an ordered pair, they say like 3, 5. You guys all know that means you go over 1, 2, 3. So 1, 2, 3, and you go up 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And you would put a point. And that would be our first point of this function. And then we could just make I would just make it up and, we could go from there. So just keep in mind, usually this is the independent and this is the dependent. So that's just the way we do it in math in general. Somebody could come along and say they wanted to do it the other way, and that would be fine too. The only problem is everybody else would have the flip of you at all times. So this is just kind of the accepted way that we do it. The dependent variable is a function of the independent variable. So if x is the independent variable and y is the dependent variable, write your function as y equals f of x. So this basically is saying that instead of saying y equals 2x plus 3, we're now going to say f of x equals 2x plus 3. In general, there's no difference. For the most part, you can always think of f of x as y, but they just want to give it more notation than just y. F of x allows us to say, well, what if I wanted to do height based on time? Or then I would call that, we could call that, instead of f of x, we could call that h of t equals 2t plus 3. What if I wanted to talk about, velocity with respect to time? I could say v of t is equal to 7t minus 8 or something like that. So you guys understand that this notation is a little bit better than just y equals, because it allows us to kind of describe what we're working with. And I want you to keep in mind, when I'm writing this, like let's say over here, let's say I'm writing h of t, or let's say s of t is equal. So this is a normal position function formula. Let's say that it's 3t squared plus 7t minus 16 or something, just making it up. So what this is saying is that s equals the position. Okay, so I would name like, oh, s is the position function, and then the position, and then t is the time. And whatever variable is on the inside of this parenthesis, we usually consider that the independent, not usually, we always consider that the independent variable. So in this case, this would be the independent, and this would be the dependent. Okay, so when you write something in function form or functional notation, you have to keep in mind that whatever's inside those parentheses, this is not saying s times t. Don't think of it that way. It is saying s of t. Why can't I erase it? This is saying S of t, meaning S based on whatever t is, okay? So that's why they say right here, if X is the independent variable, Y is the dependent variable. So it says it is a function of the independent. Now, again, there's a little bit of gray area to that because I could just as easily write X of Y and call that my F of X. And then in that case, or call that my F of Y. And then in that case, X becomes the dependent and Y becomes independent. So there are ways we can mess with the system a little bit and change things, but in general, we're not going to try to go crazy like that. The reason I like functional notation better than just saying Y equals is functional notation basically describes what you're working with. So in this case, if we are talking about S, we could also have called it H of t is equal to 7t squared minus 3t plus 1. And in this case, H stands for height. Oops. H stands for height, and this stands for time. Okay, so that way I can kind of just describe to somebody. If we were doing a cost function, I could say C of X is equal to, like 7, X squared minus 3X plus 1. And in that case, this is the cost, and this is the price. Or no, I'm sorry, not price, it's the number of items sold. Okay, so these are just all these ways that functional notation is just so much better than saying plain old Y equals. So just keep that in mind when you're looking at this. Is functional notation is actually better than saying Y equals, but it's not. That's not there is to it. All there is to it, but that's kind of a big deal for us. So let's just do a few practice examples here. So for each situation, express the given function in words. Write the two variables as an ordered pair and write the function in with the notation y equals f of x. So normally I erase this and then we fill it in the video, but they kind of did a pretty good job of describing it. So I wanted to just leave it this time. So it says you are riding in a hot air balloon. As the balloon rises, the surrounding atmospheric pressure decreases. So what they're basically telling you is based on the height of the balloon, the pressure the pressure will change. So that makes, to me, the pressure being the dependent variable, and that makes the height of the balloon the independent variable. So in here it says pressure is the let me use red. Pressure is dependent variable, okay, and the altitude is the independent variable, okay? So the ordered pair would be altitude to pressure. So we could say X to Y, or, if you wanted to do something else, you could say A to, what do they say, P? A to P for pressure, right? So you could write it either way. So it says let A stand for the altitude and P stand for the pressure. Then we write the function as P equals F of A. So once again, you're rewriting P and you're saying that it will equal the pressure, okay? But what's another way to say pressure based on altitude? F of A, okay? Or you could even say, I would probably write it like this, P of A, myself personally. I would say pressure based on altitude, okay? So that way I know this is pressure, and I know this is my altitude. And the lettering just kind of helps me make it so much easier. I mean, math is already hard enough. Why do you want to confuse yourself? Why not use the letters to represent the things you want to talk about? So I'm a big fan of that in algebra, is using letters to represent what you're talking about. Some people get confused and they just always want to use X and Y, and that's okay, but then you're kind of limiting yourself, okay? So let's go on down to here. It says you're on a barge headed south down the Mississippi River. You notice that the width of the river changes as you travel southward with the current. Okay, so let's see here. The barge headed south down the Mississippi River. You notice that the width of the river changes as you travel southward with the current. So the river width is changing based on how far south you go. Okay, so that makes the river width dependent, and the distance from the source is independent, okay? So basically, you can always tell me how far south you've traveled, right? You can always tell me how far south, or I'm sorry, you could tell me, hey, I'm, 2 miles south, and you could say, oh, well, then I'll know the width of the river based on this function, okay? So once again, they say let D represent the distance. So we're gonna say D is the distance, And then we're going to say W equals width of the river. So now they're going to say that the width of the river is equal to the function based on the distance. Now, again, I would prefer, so me personally, I would prefer to say W of D is equal to something, and then we'll have to come up with something. But I think the reason they're writing it as F of D is they just want to show you that you could rewrite width as F of D as a function of time. So literally think of this as saying width as a function of, not time, I'm sorry, distance. I'm so used to using time. Width as a function of distance. So whatever the distance is, I can then project or tell you what the width of the river would be. Okay. So representing functions, there are three basic ways to represent a function. You can use a data table, draw a picture or a graph, and write an equation or formula. This is the one we use a lot in algebra, but graphs come up huge in algebra classes as well. A lot of times we do use tables in the beginning stages of graphing functions, and then later on we kind of progress to transformations and things like that and memorizing like a library of functions. So the data table kind of starts to fall off. But I would say this is kind of like the core, or this is like your concrete, because you can actually see it happening. You can actually see when you're building a table and then making a chart and then plugging it into a graph. So these two to me go hand in hand. You use the data table and then you draw a graph, or you look at a graph and then you kind of figure out what the table would look like. And then when you progress, then you start saying, well, the equation or the formula, I know what its picture would look like. And I also know what the data would look like. So for me, the equation is kind of the progression of the first two. It's kind of like it ties everything together. And you start getting better at math when you can kind of associate all three of them together in your mind. You start seeing the overall grand scheme of the problem. Okay. So domain and range. The domain of a function is a set of values, the independent variable that both make sense and are interest of the function. The range of a function consists of values of the dependent variable that correspond to the values of the domain. So a kind of a classic example is they do stuff like this and they say this is 1, 2, 3, and 4, and this is 5, 6, 7, and 8, and this is, let's say, some f of x mapping. So what I'm going to do is I'm going to map 1 to 5, 2 to 6, 3 to 7, and 4 to 8. So what this is telling me is that this is in fact a function. And once again, I don't know if you guys remember all of this from algebra. But if something is a function, it would pass the vertical line test, right? So if I were to graph this, I would go over 1, up 5. I would go over 2, up 6. I would go over 3, up 7. I would go over 4, up 8. And then this would be this, and this would pass the vertical line test, right? Because I draw the vertical line and it never touches more than once anywhere I draw one line. So this would pass it. Now, more than likely, this is just a limited domain. If this were linear and I gave you like all the values, you would be able to connect the dots. But because you are only given 1, 2, 3, and 4, this is your domain. And I shouldn't say this because you're only given that. But we can't connect the dots because we don't have all real numbers as our domain, or we're not allowed to, fill in the blanks. The domain would have to look slightly different. In this case, this is our domain, and this is called our range. Some books will even call it the codomain. But for us, this is our range, this is our domain. In general, you guys, we oftentimes, and this is always the independent, and this is always the dependent. Okay. Usually for our class, or I'm sorry, usually you always associate X's with domain and Y's with range. Again, there's a lot more to this, but in our book, we're not going to go too crazy on that. But another way to think about it is this is what you input. This is what you output. Okay. So also you can think about this as what we are allowed to use with the problem / independent variable. Okay. And this is output Another way to think about this is what we are able or allowed to get out as a result from the function. And this is normally the dependent. Okay. So, and again, it doesn't have to be numbers. It could be birthdays. We could say, you know, like David, Jake, and Helen. And then over here, we could have birthdays in the month of October. So B days, month, or let's do November. And then let's do students. Okay, so let's say the 16th, the 21st, and the 29th. So boom, boom, boom. So in this case, the domain would be David, Jake, and Helen. Oops, Helen. And then the range would be 16, 21, and 29. Not all the numbers between 16, 21, and 29, but literally only 16, 21, and 29. Those are the only 3 days of the month that have birthdays on them from this group, okay? So the domain dictates what the range can be, okay? So a lot of times in a lot of math algebra classes, the domain turns out to be much more important in finding than the range. And that's because if you find the domain, then it dictates the range. And once again, the domain has to do with the independent variable and the range has to do with the dependent variable. So you could see how that could work, okay? So let's see how much we have left here. Oh, just about 3 more pages, okay. So creating and using graphs, identify the independent and dependent variables of the function. In general, like I said, use the x-axis as the independent variable. In general, that's how we do it. Identify the domain and range of the function. Use the information to choose the scale and labels on the axis. Axes. Zoom in on the region of interest to make the graph easier to read. So, you know, like if they're talking about, you know, using millions or billions or whatever, and you're only concerned with a certain section, you can kind of zoom in on that area. Make a graph using the given data. If appropriate, fill in the gaps between the data points. Before accepting any predictions of the model, be sure to evaluate the data and assumptions from which the model was built. Okay. So let's take a look at this. The number of hours of daylight varies with the seasons. Use the following data for 40 degrees north latitude to model the change in number of daylight hours. So they're basically saying changing the latitude changes the number of daylight hours with time. Okay. So the number of hours of daylight is greatest on the summer solstice around June 21st, when there are about 14 hours of daylight. The number of hours of daylight is smallest on the winter solstice. So they're giving us this information. This is being given to us. The number of hours of daylight is smallest on winter solstice around December 31st solstice, when there are about 10 hours of daylight. On the spring and fall equinoxes, around March 21st and September 21st, respectively, there are about 12 hours of daylight. So it turns out, it looks like right here, 14 hours of daylight is pretty good. So if you have solar panels, those are the months that you probably have the most sun because you're getting the most sunlight. And then the months that you're getting the least amount of daylight is in December, right? Now, not only is it probably raining more, but that seems like more so the problem is the number of hours of daylight, not necessarily the rain. Obviously that would hurt too, but you know, if you're thinking solar panels, you should, you know, this is just one, just because I have solar panels, I'm just bringing this up. You should expect to get a lot better energy production in these months, not just because it's hotter and there's less rain, but also it coincides with the days are longer, so you have more hours of daylight. Okay. So then it says, since time passes regardless of other events, let time denoted by t be the independent variable. So we know that t equals time is going to be our independent, which makes a lot of sense. And I will tell you guys, in general, If you're working with time, it's almost always going to be the x-axis, the left and right axis. It says let the hours of daylight denoted by h be the dependent variable. So h equals hours of daylight. Let that equal that'll be h. Okay, so now we know that we're working with the function h is equal to f of t, or we could even write it as h of t, the number of hours based on time. Okay, the domain is all times of interest. Let's just say we're going to work with the first 3 years that we're talking about here, or we're going to work with a 3-hour window. The range is from 10 to 14 hours. So we see the lowest is 10 hours to the highest of 14 hours. And the number of hours of daylight changes smoothly within these seasons. So we are not going to be worrying about like sharp edges like this. It's going to be something like this. They're saying it's smooth. Okay. The same pattern repeats from 1 year to the next, called the periodic function. So now periodic functions, now that starts making me think of sine, cosine, and tangent. The sine function does this. That's what the sine function does, or the cosine function, depending on where you start it. So we're thinking of something like that. They said it's smooth. So that's also kind of nice. Okay, so, and there you go. Sure enough, look what we get. So it says this is a graph of the function of h equal to f of t shown below. So here we have, this is the t-axis, and this is the h-axis. Now I know you guys are used to seeing this as the x, and this is the y, and I'm still doing everything the same. I'm still saying that x is the independent and y is the dependent, but I want the letters to represent what we're talking about. So I'm going to call this the t-axis, and I'm going to call this the h-axis, even though in our minds we know it's the x and the y-axis. Okay, it's just a good way to help us work with problems. Okay, so it says here, so for example, they say so they're doing everything in terms of days, so you can cut it up if you want. So this is 365 is the first year, double that, that's 730, triple that, that's 1095. So they're basically just doing 3 years for us. Okay, now let's see here. If we wanted to know, information now, we could look here and we could say the summer solstice is 172, right? 172 days. And they're saying that would be when? Around in June, I believe they said up here. June 21st. So more than likely, we don't know this exact day, but they're saying that this is more than likely probably June 21st or somewhere in that range. Because once again, and it makes sense too, because June is halfway through. June 21st is about halfway through the year. So this is probably what they're referring to. So we could then say that this is the coordinate, 172, 14, right? That would be our coordinate. And then this coordinate, if these are going by what does it look like they're going by? 92? I think they're going by 92-ish. Oh, they're not quite perfect. They're just kind of doing it how they want. Okay. Well, if we had to estimate, what's halfway in between here, I would say 365 plus, let me get my calculator so I don't mess it up. So let's say 730 plus 365 divided by 2. So I would say this is about 547 days, maybe 548 because I rounded off. So we'll say about 548 maybe. And then this would be 548, 14 once again, right? I do that really bad. Sorry about that. 548, 14. So we could find all these coordinates for here if we wanted for each one of those based on this graph. And it's important that we labeled this T for years and this for height. So now when we know we're finding height based on time, or I'm sorry, hours based on time, it's pretty easy to find. We just got to figure out the labels and everything and kind of follow their pattern. But in general, it's not normally horrible to graph functions. Functions behave nicely. Also, remember I had mentioned earlier in the video, the vertical line test. See, I can draw a vertical line anywhere on this graph, no matter where I want to draw it. And I will always only touch the graph one time with a vertical line. That's another way to recognize if a graph is a function, is if it only touches the vertical line once. That's because to be a function also, we don't want to, I know your book's not going too crazy into detail of this, but functions have a very specific behavior. Functions basically can never have one X value with two separate outcomes. So that's kind of a determining factor if something's a function or not a function. There's all kinds of graphs out there. I mean, look at a circle. Here's a circle. Now a circle is a cool graph, one of the best shapes in mathematics, but it is not a function, right? Because it does not pass the vertical line test. If I draw a vertical, oops, let me do it in blue. If I draw a vertical line right here, I touch here and I touch here. That means it's not a function, okay? You cannot have a vertical line that touches a graph twice and it be a function. Now it can still exist and it still can be something, but that's because let's say that this X value is 2 right here. That means that when I go to graph these coordinates, this would be like 2, -1, and this would be like 2, +1. And again, my graph is terrible. This red should be like, like that. So don't get too caught up in my graph. But again, our book's not going to go too in depth into that. We're not going to go crazy on functions on the in class. What we're more concerned with is being able to work with the notation, being able to understand what the notation means and what it describes for us and how to use a graph from it. Okay, so there's quite a bit of homework problems on the maybe 2 or 3 on a graph, and then a lot of like information and asking you questions about independent and dependent variables. But that's going to do it for this video, you guys. Thanks for watching, and I will see you in class.